Hello scholars and welcome back to Mr. Sniffen's geometry class. This is Harvey here. Today we're going to be talking about a special type of quadrilateral known as a parallelogram. It's kind of the name implies one of the interesting characteristics of a parallelogram is that all of its opposite sides are parallel. In addition to that, they're also congruent. Knowing these two specific factors in geometry, it ends up generating a plethora of characteristics that are required to happen. So let's take a look in our notes for today and see what's going on with this special quadrilateral. Along top of the page here, we have our definition for a parallelogram. It is a quadrilateral where our opposite sides are equal and parallel. The way that we normally express this in terms of a diagram is with some of the various charts here on the left-hand side or notations. Let's take a look here. In our first diagram on the left here, we're using hash marks to indicate congruency, meaning that this side here on the left and this side here on the right are equal in length. They're exactly congruent to one another. Our arrows, as we've seen in previous lessons, dictate that these two lines are parallel, or that if they were transposed onto a graph, their slope is going to be the same. We can also describe that as kind of the angle that it makes with this line along the bottom here. If we follow this characteristic where now our additional pair of opposite sides is also congruent and also parallel, we end up generating a set of interesting rules. So just to let you know as well, this figure here is a little bit different than a rhombus. Our lengths on our opposite sides are congruent, but all four are not congruent. We can have super long sides with very itty-bitty paired opposite sides as well too. So it's not exactly like a rhombus or a square where all four sides are congruent, but we have this kind of feeling that it starts to look like that. With our quadrilaterals, the more and more specific we define our shapes with rules like our opposite sides are equal and parallel, the more variables we kind of can remove. We only have certain specific systems of consistency that end up getting generated. So let's look at some other ones here. Whenever we have a definition of a parallelogram, we know that this left-hand diagram is always a fact. What also gets generated from this statement is that we end up having opposite angles which are also congruent. The way that we dictate congruency for angles is with these arcs in the corner. The double arcs represent these two pairs are congruent, and it's a different angle value than these two acute angles in the bottom left and top right corner. In addition, what ends up happening, because of these congruency pairs, we end up getting diagonals which, when they intersect in the center, they get split, or what we would call bisected. So this portion here ends up being equal to this portion, this bisected diagonal, and this diagonal going from the bottom left to the top right also has two bisected pairs as well. So knowing all these different rules allows us to kind of generate different types of mathematical statements that allows us to solve for variables and unknowns and things like that. Furthermore, if we wanted to, we can also, as you see here, kind of break down things into triangles, and we get different triangle-based rules as well that we can construct. So the more and more rules that we know, we can actually parlay that into other shapes as well. But let's take a look. Let's add to our notes here. So as opposed to just remembering, say, the diagram, if we're told that we have a parallelogram, or if we go about and use deduction and figure out and calculate sides, we can know that all of these statements here are true. So let's take a look. First one being directly from our notes, our opposite sides are going to be congruent, which is dictated by those hash marks. We can also say our opposite sides are parallel, and remember that those two L's basically dictates parallelism. We'll use the abbreviation para for parallel, OPP for opposite as well. We can also say, like in our diagram in the middle, our opposite angles are going to be equal as well. When we use the equal sign, we're talking about numerically, like 95 degrees equals 95. And look at this cool rule here as well too. Adjacent angles are supplementary. If you don't remember, supplementary means when multiple objects add up to 180 degrees. If we take a look at the diagram here, we can see how if we add this angle plus this angle, we end up coming back to these parallel lines. So between two parallel lines, there's always 180 degrees because you have to make that big, huge loop right back around, say just like half a circle, where you're walking around the block. You say you're walking down 59th Street, you go up 2nd Ave, make another right, get back to 60th Street. You're now parallel with where you once were, but you did a 180-degree turn. You did two 90-degree turns. Lastly, for our notes here, we can say that our diagonals bisect each other. And once again, that kind of is indicated by this third diagram on the top right here. Let's take some examples of how we would see this represented in, say, a math textbook or some type of questionnaire, or similar to what you're going to see in Delta Math later today. So I have 3 parallelograms drawn here along the bottom. They're actually all duplicated. I used a safety compass to kind of generate and create all of these along the bottom here, but I randomly assigned values to everything. In our first parallelogram here, and of which we're told we have a parallelogram, so we know that we can use these rules here, we're told that along the top here, AB is equal to x plus 7. And based on our rules, we know that AB is congruent or equal to our opposite side of DC. If we want to go ahead and set up an equation, we would say x plus 7 is equal to 29. And we just subtract out, and we get 22 for our x. Let's take a look here at our second diagram. In our second diagram here, we're told we have a parallelogram, so we know that our adjacent angles are always going to be parallel because we're able to wrap back around. So we can say that the measure of angle D plus the measure of angle A is equal to 180. Substitute our values in for angle D. We know is 35 plus, we'll say our unknown of x is equal to 180. Subtract everything out, and we end up getting a value of 145 degrees equal to x. One thing that we could also say in this particular example, since we have a parallelogram, we could also theoretically solve for angle B and say that's 35 if we wanted to. Since we have another pair of opposite angles, we can also go ahead and say that we got 145 as well. So 35 plus 145 gives us 180, 145 plus 35 gives us 180, so on and so forth. All right, let's finish up with this last example on the bottom here. We have another parallelogram. This time we're looking at basically that third diagram when we're talking about our bisected diagonals. Here I added a point in the center so we can describe segment AE as equal to segment EC. And if we just go ahead and fill in our values, we could say 23 is equal to x plus 10. Subtract everything out, and we get a value of 13 equal to x. So one other thing to note here, just so you're sure of this, DE is not congruent to AE. We do not know any value associated with DE or subsequently EB. We can go ahead and, if we had another side here, we can start to work out some type of Pythagorean theorem using sine, cosine, tangent, these types of rules as well. But DE would only be congruent to AE if we had a rhombus. Because in a rhombus, our diagonals in a square, our diagonals end up being congruent, as well as in a rectangle, their bisections end up being equal as well too. All right, so here are 3 different examples of how you would normally see parallelograms presented in some type of question and answer scenario, say like on a Regents exam. Oftentimes you're going to be presented with multiple step questions, particularly if it's on like your end of year Regents, for example. You would be solving for, say, A, and the question is actually what's the value of C, so you have to know that additional rule of the opposite angles, things like that. But for your work today, once you finish up with your ed puzzles on delta math, primarily the questions are associated with this guy here in the center, talking about angles themselves. Today is Thursday, so that means tomorrow on Friday you're going to have a short assessment. It's going to cover some information from video 1 in terms of kind of usefulness of math, or what some of these vocabulary terms might mean in terms of like binomial, or vocab from Tuesday as well. Some questions from yesterday in terms of solving for supplementary, complementary angles, and then this stuff that we went over today. If you have any questions, please feel free to stop by office hours. Be more than happy to help talk to you, hang out, do whatever you want. If you got questions, also feel free to text me or email me. But until next time, have a nice day. Enjoy your Thursday. Hope to hear from you soon. Bye.